anything but a conformal similarity, I would have thought you were pretty great. And yet, I find myself today advocating that really, we should think of this as a single field. We're essentially asking the same questions. We're using very related methods. We have a huge amount to learn from each other in these seemingly distinct fields, condensed matter, quantum information, quantum gravity. And today's speaker is someone who understood this many decades earlier, and whose work really lies at the foundation of what has led to this confluence, this breaking down of barriers. And so here at STAT, so Cardy got his PA and PhD in Cambridge, England. He did postdocs at CERN and Santa Barbara, and he became an faculty there at UCSD, and later went to Oxford. He's won a lot of prizes. Let's just say that there are 2 Girac medals. He's won them both. We really hit the jackpot because Don is here not just for this semester as a visiting Miller professor, but he has actually moved to California, and so we believe that we'll have him here for much longer than that. That leads me though to my point of constructive criticism. Unfortunately, there's only one of them, and the condensed matter group and the particle theorists are still in different buildings. And so that has led to a bit of a tug of war between us and our former friends, Joel Moore and Ashton. And so who gets to spend more time with John, so if you could please also clone yourself, then we will be really happy. But meanwhile, welcome to Berkeley, and we look forward to your collaboration.
Okay. Thank you for that very nice introduction. And I should say that I will try to spend more time over there. The previous 2 institutions that I've been in, of course, the theoretical physicists were all in the same building, and we intermingled our offices. And I should maybe, if there's going to be some forward planning in this department, maybe that's something that you might aim for in the future. Anyway, I'm going to talk about the subject of quantum quenches. So there are 2. This is a very alliterative title, as I'll explain. Of course, most of you think you know what quantum physics is, and you may have an idea of what a quench is, but I'm going to spend just a few minutes making sure that my use of the word quench is the same as what you are actually thinking about. That is, we might be going out afterwards to actually quench our Earth, but that's not what I'm actually thinking of. So this is an example of what I call a thermal quench. When I was in high school, we did something which I think over here is called shop. Over there in Britain, it was called metal work, and I'm afraid in those bad old days, the metal workshop was only done by the boys, and while the girls did other things like more useful things like learning how to cook. But those were the bad old days. And anyway, so I learned how to make a poker. And the way that you make a poker is that you get a piece of steel iron and you heat it up in a furnace, and you bash it into shape while it's in a a semi-molten state, and then you want to cool it, of course. But if you let it cool naturally, what happens is that it becomes brittle. And the reason that it becomes brittle is that it goes through a phase transition and various crystallization processes happen that you don't want to happen. So what you do is to actually cool it very quickly by plunging it into a vat of water, and that sort of freezes the impurities and so on into the positions that they were in at the higher temperature. So a quench is basically a very, very rapid change in the external parameters, a temperature, whatever, of a system, and in such a way that it doesn't come into equilibrium, at least in a thermal quench. I'm going to contrast this with what actually happens in a quantum quench. So what I've done here is to illustrate for you a schematic phase diagram of a material. For example, it might be a magnet, and the parameters of the Hamiltonian in this magnet in general depend on a coupling constant G, which might be the interaction strength, it might be an external magnetic field, and so on. But let's suppose that for the time being, that for small values of G, if you heat the system up, quantum mechanics is not important. It's the thermal fluctuations which are important rather than the quantum ones. And we can imagine that this system has a critical point, for example, where it goes from a ferromagnet to a paramagnet, and this would occur at a critical temperature Tc. And a quench is, for example, if we quench the temperature very quickly so that we're in the paramagnetic state, and we quench it very quickly down to a temperature in which it would be in the ferromagnetic state, except it may not have had time to come into equilibrium. So that's an example of a thermal quench, and these red arrows illustrate the kind of thermal quenches that you might consider doing. You might do a quench from the disordered phase to the ordered phase, for example, or what would be the ordered phase, except it can't come into equilibrium, or from the ordered phase to the critical temperature, etc. Now, down here, I illustrate what is happening in a quantum quench. And first of all, if you follow the phase boundary down, you might find that there is a critical value of the coupling constant even at zero temperature, where you have a phase transition as a function of the coupling constant. So this is an example of what we call a quantum phase transition, and nowadays we have lots of examples of these, both theoretically and in the lab. So a quantum quench is when it's the quantum fluctuations are important rather than the thermal ones, and you imagine rapidly, as quickly as you can, changing a coupling constant, which I remind you might be an interaction, an exchange interaction, it might be an external field, etc. But the main thing to learn from this is when we're talking about quench dynamics, we are thinking about changing the external parameters in a very sudden way, and that's in contrast to what would happen if we made what we call an adiabatic change, when we would change the coupling constant very, very slowly, such that at each value of G, the system had a chance to come into equilibrium or get into its ground state. So that's a quench, and of course the idea of a quantum quench has been around for a very, very long time. Certainly, it's the sort of thing that people were doing in atomic systems, you know, changing some external magnetic fields for quite a long time. But for reasons that I'll explain in a moment, people became interested in this more deeply in the around 2005 or so, and my collaborator Pasquale Calabrese and I wrote a paper on this in which we actually coined the term quantum quench. I mean, I don't mean to actually say that this was the first paper in which a quantum quench was considered. It certainly wasn't, but this is an interesting illustration of sort of social dynamics in physics, because if you give a phenomenon an interesting name, that name sort of sticks to it. So the fact that this was a nice alliterative name actually stuck, and in fact I recently did a search on the archive for the term quantum quench, and you probably can't read it there, but I searched and for quantum quench, and it says 322. That's not that many, really. 322 papers on the archive since then, which contain the words quantum quench, and you see, as Raphael said, some of these are in condensed matter. I guess most of these are, but you will also find papers on quantum quenches from people who do ADS and gravity and all kinds of interesting subjects like that. So the point is, in a thermal quench and a quantum quench, the dynamics is actually completely different, and the kind of questions that you're going to ask are correspondingly. So if you take a thermal quench, you change the external parameter quickly. Various processes happen rather fast, but then you soon get into what's called classical relaxational dynamics, where the characteristic motions are basically diffusive, and you get very slow coarsening phenomena eventually reaching some new equilibrium state, though it may take a very, very long time to actually do so. In a quantum quench, on the other hand, this is quantum mechanics, so the system is evolving according to the Schrödinger equation, and I can't stress that too much. The whole point about a quantum quench is that the system is not coupled to an external bath and external reservoir. It is evolving unitarily, we say, according to the Schrödinger equation, so that if the system starts, for example, in a single pure quantum state, it remains in a quantum state. It can't go into what we call a mixed state, which will be typical of what would be happening if you were at finite temperature. So if you ask what is going to happen after a quantum quench, is it possible for the system to come into some kind of equilibrium, some kind of a steady state? Well, the answer is, well, not really, because it remains in a pure quantum state. It doesn't look like it's in thermal equilibrium. Nevertheless, we will actually see that from some points of view, in a very well-defined way, it does come into thermal thermal equilibrium, and that's why it's interesting. Okay, so even though all this dynamics is happening at 0 temperature, the system's going to end up looking like it's at finite temperature, which is very interesting and curious.
These all quenches through transitions, which would otherwise be second order.
Yes, more interesting things would happen if you quench through a first order transition. And I should also say that in the rest of what I'm going to actually talk about, I'm going to look at quenches to the critical point, so to a second order critical point. And there's no particular reason for that beyond the fact that those are the calculations I can do with the tools at my disposal. Okay. So, okay. So, now the point about one reason that lots of papers weren't written about quantum quenches before about 2000 and whatever is that in a solid state system, these questions are just not interesting because the timescales, if you have a magnet or electrons in a solid, the timescales are just too fast. And moreover, these systems never evolve unitarily, at least for an appreciable time, because they're always coupling to a bath there if it's phonons or whatever. So you don't actually see this. But in ultra cold atoms, you can actually do this. First of all, the timescales are much slower. You can isolate them effectively because there aren't necessarily. If you put ultra cold atoms, for example, in an optical lattice, there just aren't the phonons there. And moreover, it's possible to actually switch the coupling constants, for example, some external field very, very quickly. And the other thing is we will see in certain examples that you can do, for example, direct imaging of the observables rather than doing a scattering experiment, for example, where you only look at correlations. So I'm going to give you one example here, though there are many, and this is rubidium atoms in a one-dimensional optical lattice. So you imagine that you have these atoms here. The optical lattice is basically a periodic potential in which the atoms want to sit, and the atoms can also hop, right? So depending on the size of the peaks in this potential, or rather the depth of the wells, they'll either want to sit in the bottom of the wells, which is called a Mott insulating phase. It's insulating in the sense that the particles can't move, or a phase where the particles where the particles move, and because they're bosons, this is basically either a superconducting, or you can call it a superfluid phase. Okay. So, and it turns out this system is very well described by what we call the Bose-Hubbard model, which is a boson version of the Hubbard model, which describes electrons. And so these are basically, we have a regular lattice. The minima of this potential are labeled by an integer j. I've just drawn it in. Basically, you can do this in effectively one dimension. So A, J, and A dagger J are just ordinary boson annihilation and creation operators. So this term represents hopping of these bosons between adjacent sites. And the Hubbard U term here, so A dagger J, A J is the number operator at each site. Its eigenvalues tell us whether there are 0 particle, 1 particle, etc. And this term says, well, it's going to cost us energy because U is positive. It's going to cost us energy to have more than 1 particle at each site. So this Bose-Hubbard Hamiltonian is obviously, what's important is the ratio between U and T, which we call G. And if G is much bigger than 1, we're in this Mott insulating phase. Much less than 1, the superconducting phase. There's a quantum critical point for a particular value of G. So the experiments that were done that I'm going to describe involved a quantum quench from G much bigger than 1, that's in the Mott insulating phase, to the critical point. And I don't usually include diagrams of apparatus, but I thought I would here just because it's kind of nice what they do. This is holography, so it's not the kind of holography that my quantum gravity friends usually talk about, but this is real holography. So there is a hologram here, and they use various optical systems, and this one produces the lattice pattern here. There's another one which produces the overall confining trap. And the nice thing is that once you've done the experiment, you can actually reverse this optics to actually read off what you can actually see there. So it's a very nice experiment because you can actually directly image what actually happens. So the protocol, as I say, it's a quench from large G to small g. So you adiabatically, very, very slowly, prepare a state with extremely high barriers. So you try and make sure that the system is really in its ground state with G bigger than 1, with 1 atom per well. And then you quench very quickly, and then you let the system evolve in isolation. And then, of course, you've got to read off somehow what you've got. So the way they actually do that is to once again rapidly increase the barrier height, and that freezes in however many particles are at each site. So it's at this point that the quantum measurement is actually taking place. And of course, this is quantum mechanics, so that even though I start with a nice simple state, when I evolve this with a Hamiltonian, I will evolve into a superposition of states. So when I make my quantum measurement, I don't always get the same answer. That's quantum mechanics, right? So that's important here, right? So, and then once you've done this, once you can actually read this off. And there's an interesting twist to it, though, which is just to do with the properties of these rubidium atoms. When you actually shine the light on them, they tend to form molecules, which means that you can only actually tell whether there was an even number or an odd number of atoms at each site. So you can, in fact, observe only -1 to the end, but that doesn't really matter all that much. So in order to get statistics from this, of course, you have to repeat the experiment again and again, and because of quantum mechanics, you get a different answer each time, and you have to compile the statistics. So here's an answer, and I haven't made a mistake here in actually putting the diagram on its side, and you're not supposed to stand on your head to read it either, but as in the rest of the talk, I'm going to have time going vertically upwards. I thought I would rotate the experimental plot. So what you see here are plots of this correlation function at the same time t, but at separations d. So this is d equals 0 as a function of time d equals 1, d equals 2. So this could be done as a contour plot, but it's not. Okay, so what you see is that at d equals 0, there's a small correlation, then you get these oscillations, and you go into something sort of noisy. The important thing is that you see this sort of straight line running across here, and this is more illustrated here, which is an intensity plot illustrating exactly the same data. So there is some kind of ballistic motion here. That's the main thing to realize. It's ballistic, it's not diffusive. Okay. And you also see that after this sort of wave has passed through, there are kind of interesting noisy oscillations going on. That is, the state that's left after the wave has gone through is some kind of interesting fluctuating state, and we're going to claim that that looks pretty much like a thermal state, even though this is quantum mechanics at 0 temperature. So that's all I'm going to say about experiments. I'm going to talk now about how we treat this theoretically. So then we want to have some kind of idealized setup. So we imagine that we have some extended quantum system at initial time t equals 0. We're just going to assume, just to make it simple, that it's translationally invariant and it's a pure state. So really what we try to do is to get it into the ground state of this initial Hamiltonian before we make the quantum quench. And then after the quench, we change the Hamiltonian to the Hamiltonian H. Psi 0 is no longer an eigenstate. And the other thing is that it's likely to have, well, it's bound to have a higher energy than the ground state of H, because you can always think of psi 0 as being some kind of variational trial state for the Hamiltonian H, and it must have energy, therefore, above its ground state. So you always put energy into the system when you do one of these quantum quenches, and moreover, it has extensive energy in general. That is, the energy is proportional to the volume. And one thing is that we're going to assume very, very simple translationally invariant Hamiltonians, something like a quantum spin chain with just very, very, very simple quantum dynamics. So I'm not going to be talking, as you might have heard in this series before, about many-body localization, which is very, very interesting, but the dynamics there is completely different. So I'm not going to be talking about many-body localization. And the kind of questions that you would like to ask are, okay, how do correlation functions evolve as a function of time? Because this is quantum mechanics, quantum entanglement is extremely interesting. It turns out that the states that you start with are ground states of the Hamiltonian. They typically have very low entanglement, but the entanglement then sort of grows, because a typical state has actually very high entanglement. So you would like to know, how does the quantum entanglement grow? If you, as I said before, the system starts in a pure state, it always has to stay in a pure state, doesn't become stationary. But nevertheless, the right question to ask is, if you look at part of the system and ignore the rest, does that become stationary? And the answer is going to be yes. And then the question is, if so, what is the stationary state? Is it thermal? Well, I'm going to say in the kind of calculations we do, yes. How do you get there? How does quantum entanglement behave? And if you have not an infinite system, but a finite one, can you get quantum revivals? That is, does the system ever actually go back all the way to the initial state? And that's been observed experimentally too. In a small system, you're always going to get these quantum revivals. And then an important theoretical question is, it's going to turn out that we can only really do these calculations in models that we can solve. So is the fact that we can solve these models influencing our interpretation of the answers? What happens in models that we can't solve? Well, we look under the lamppost. You've probably all heard the story of the guy who's lost his keys in a parking lot, and he's looking under the lamppost, and somebody asked him, why does he look there? And he said, because that's the only place I'm going to find them. And we look at integrable models because that's the only place that we can find the answer at present, but I hope that's not always going to be the case. Okay, so what are the theoretical approaches? Well, traditional methods that you can read in a normal textbook on solid state physics or condensed matter physics really just don't work. So numerical methods, well, what you're trying to do is to solve the Schrodinger equation with 1,000 particles there. And really, the system is acting like a quantum computer in a way. So you're trying to simulate a quantum computer on a digital computer, and that doesn't work very well. Okay, so those are difficult, but not impossible. So we're sort of down to models that we can actually solve exactly like sort of integrable quantum spin chains, quantum field theories, but I'm going to focus on conformal field theories, and that's firstly because they're the sort of easiest kind of integrable models which show the kind of phenomena which are interesting, and first of all, and secondly, that's something I know a little about. Another interesting approach that I won't talk about, but which has been useful, is this ADS CFT correspondence, and there are interesting complementary results to ours that come out of this approach. So what we did in 2006 was to study this problem when the Hamiltonian is that of a conformal field theory, and we start with a state which has short-range correlation. So a conformal field theory describes the long wavelength properties of a system at a quantum critical point. So we're looking at a quench 2, a quantum critical point, and by assuming that our Hamiltonian is just that of a conformal field theory, we're somehow assuming that this is a good description of the system, not just at large wavelengths or low energies, but also at higher energies too, which is not necessarily justified. Now, most of you in the audience probably don't know very much about conformal field theory, and you'll be very glad to hear that you don't need to know anything in order to follow the rest of the talk. Okay, so I'm just going to tell you that it does describe these kind of systems, in particular that one-dimensional Bose-Hubbard model that I told you about, and the kind of results that we get don't depend on very detailed properties of these conformal field theories, only very general properties. The analyticity properties that really come out of the fact that these things sort of look relativistic. So even though they are describing condensed matter systems or cold atom systems, they look like they're relativistic. That is, everything travels at the same speed, which in a relativistic theory would be the speed of light, but now it's Fermi velocity or something, or the speed of sound or something. Okay, so they have this property that the excitations, which we call quasiparticles, which, by the way, in this Bose-Hubbard model, the quasiparticles are not the particles. They're sort of waves. They're quantized waves of these particles, like, for example, sound waves. Okay, in sound waves, it's not the particles themselves which are actually traveling. Okay, so these things travel at constant velocities, plus or minus v, and what makes the models solvable is that when they cross each other, they go straight through each other and don't really notice it. But so these are all special properties, but it turns out that the results that we get out of detailed calculations can be interpreted in terms of this simple quasiparticle picture that I hope to explain to you. But let me just tell you what the results are. Okay, so first of all, if you look at one-point functions, that is, if you start from a magnetized state and you look at how does the magnetization on a particular site behave, if you're talking about a magnet, then these things generically decay exponentially towards whatever they would be in the ground state, unless it's the energy. The energy itself is conserved. This is Hamiltonian dynamics. So some things are conserved. If they're not conserved, they just decay away. But it's more interesting if you look at a correlation function, for example, a spin-spin correlation function. So this is a sort of space-time diagram. This is space going across here, time here, and we're looking at the correlation function, say, between the spin here and the spin here. And initially, the correlation length is very, very small. It's very, very small on this scale, so the correlations are decaying exponentially along here. So the correlation function is just the product. So the connected correlation function decays exponentially. So initially, as you follow these points up as a function of time, things are, this just is the product of the one-point functions which decay exponentially until a particular time when this interval falls inside what we call a horizon or a light cone. So I told you that this was a relativistic, looked like a relativistic theory. So we use all these terms like light cones, horizons, even though we're really talking about propagation of, say, sound, not propagation of light, okay? So once this interval x1 to x2 falls inside this increasing cone, centered at the midpoint here, things change, and actually the correlation function becomes stationary. And once this has happened, once this interval has fallen inside this horizon, the correlation functions are indistinguishable from those that you would see at finite temperature. And it's this, in this sense, that you get thermalization. And what you can show sort of technically is that if you work out what's called the reduced density matrix of this finite system, it becomes exponentially close to what you would have if you put the system in contact with a heat bath. Okay, so, and in fact, if you work out what's called the entanglement entropy, that's the same as the thermal entropy. So this is thermalization, but not as we know it, okay? Because look, what's actually happened is that for this to happen, it's actually thermalized in the time that it takes a particle to go across the system, just one particle. So this isn't because it's exchanging lots of energy with some heat bath or something. After this time, it's just instantly thermalized. And when you go into why this has happened, it's because of quantum mechanics, it's because of quantum interference, basically. Okay, so I'm saying that this is starting from an initial state with short-range correlations. Yeah, but, and various other assumptions. So the important thing is that the initial state has a certain energy above the ground state. What determines the temperature, the effective temperature, is that if the system were in thermal equilibrium, there would be a certain equation of state between its temperature and its energy. Okay, so once you know the energy, you know its temperature. Depends on the entropy. Okay, so for that particular energy that you start with, the energy is conserved, and then there's a particular temperature corresponding to this, and that's the temperature you get. Okay, so this can be explained within this quasiparticle picture. Okay, so this is why you don't need to know all the details of these calculations. As I said, in this theory, all the excitations either travel right or left or at the same speed. And the idea is that this is space, once again, and time. Here's our initial state, and this initial state has a finite energy density, and it acts as a source. It looks like it's hot. It acts as a source of these pairs of quasiparticles. Momentum is locally conserved, so if you have one going to the left, you have one going to the right. So you have emission of these pairs of quasiparticles, and each of them, if they come from the same region of the order of the initial correlation length, are going to be entangled, quantum entangled. So I haven't talked very much about what is quantum entanglement, but you probably know. and this was recognized a long time ago as being an important property of quantum mechanics, and Einstein, Podolsky, and Rosen, in their famous thought experiments, said, what happens if you have two entangled particles starting from the decay of the same atom? One of them goes way over there, the other goes on the Andromeda galaxy, but they're still entangled, right? And if you make an observation there, if Alice makes an observation on the Andromeda galaxy, then it's going to influence what Bob measures. And that Einstein didn't like, of course, he called it spooky, but it's there. It's a property of quantum mechanics. Einstein wasn't wrong by the way. He just said this was inconsistent with a local interpretation of quantum mechanics, and the fact is that it is. Apparently, quantum mechanics doesn't have a local interpretation. Anyway, so the idea is that in this many-body system, the initial state is a source for many of these entangled EPR pairs. Okay? And then, if you think now about this one-point function, just the magnetization of a spin here as it evolves in time, then it's constantly being bombarded by this quasiparticle radiation. But at different times, these particles are coming from different places, and they're not entangled with each other. They're incoherent. So it's being bombarded by incoherent radiation. It's just incoherently flipping up and down. It's a Poisson process. And its expectation value, it decays exponentially. Okay. So that's the one-point function. The two-point functions are more interesting. So here's our interval again, and we're looking at the correlation function between its an observable, like a spin here, that I call phi and phi. So I'm going to have a sequence of 3 pictures as the time evolves. So at very short times, what happens is that quasiparticles that start from here do not actually have an effect here. The only ones which are, and moreover, these particles here cannot affect the correlation between here and here. So the correlation function doesn't change. It's just the product of these one-point functions, which are decaying exponentially. If we look at the entanglement between this interval A and the rest of the system, that's more interesting, because these EPR pairs, this one here, these are entangled, and this is hitting the region A, whilst this one is not. And so pairs like this are giving rise to increasing entanglement of the interval A and the rest of the system. And if you think about how many such pairs there are, these do it, but these ones don't, that is going to make the entanglement increase linearly with T, up to the point where these points fall just inside this horizon. And at this point, this particular pair of entangled particles causes the correlation function to change from what it was doing. Okay, and at this point, obviously, just simple geometry tells you that 2vt is equal to x1 minus x2. So the entanglement entropy at that point, which was proportional to t, is also proportional to x1 minus x2. And then if you wait for longer, then once again, the correlation function can't change because, and you can also see that the entanglement entropy saturates now. So So that gives you a very simple explanation. Of course, you might say, well, it was just too simple. It was within this particular theory where everything travels at the same speed, blah, blah, blah. But this quasiparticle description is more general, though it really only makes sense strictly in integrable models, where even the high-lying states of an integrable model can be described within quasiparticle description within what's called the beta ansatz, where each state corresponds to a certain configuration of quasiparticles. And however, this ballistic spreading of the correlations, which was observed in the experiment, is in fact more general, and it's believed to be a consequence of something called the Lieb-Robinson bound that was proved a long time ago, which says that if you have a quantum spin system, then the correlations, and whatever state you actually start with, the correlations can't spread any faster than linearly, which is rather strong result. I mean, we, of course, in a relativistic theory, they can't spread faster than the speed of light anyway, but many of the effective models that we write down to describe properties of materials are not relativistic, obviously. Nevertheless, things can only travel at a finite speed. And this is an example of a quantum spin chain where here now actually time is running down inside of it, but you actually see this ballistic spread of the correlations, and even in the non-integrable case. And what's interesting, by the way, in here, these weaker shadows that you see are the ballistic propagation of bound states of these magnons in this particular model. So you can actually see more of the structure of the eigenstates of the Hamiltonian in one of these quantum quench experiments than you can in a scattering experiment where you can only see the low energy spectrum. Okay, and then you ask the question, let's see, how much time do I have left? About 10 minutes, good. And then, of course, at some point, people say, well, I've read about thermalization. There are whole books on my shelf about thermodynamics, and I've read Landau and Lifshitz, and they explain how statistical mechanics works and why I can think about a thermal ensemble. And this is very, very different from that. So you can ask, is this real thermalization? And well, I think the answer is maybe yes, maybe no. One question to clear up immediately is this influence of integrability. So in an integrable system, that means that there's an infinite number of quantities that can commute with the Hamiltonian, infinite number of conserved quantities. So we wouldn't even expect to get a thermal ensemble e to the minus beta h. We'd expect something called a generalized Gibbs ensemble, where there's a separate temperature beta k for each possible conserved quantity. And in fact, when you go through the argument more carefully, that's indeed what you get. But I would argue this is still thermalization. It's just thermalization to a different kind of ensemble. But it's different because we don't go to a mixed state. The whole system remains in a pure state, as I said. And it happens in this ridiculously short time. The other thing is the system is integrable. It's not ergodic. It's not exploring its phase space. And there's an interesting relation that I don't understand to what's called the eigenstate thermalization hypothesis that says that if you take any sufficiently complicated system and a Hamiltonian, and you take an eigenstate of this Hamiltonian with a certain energy E, then and you just make measurements within that eigenstate as a pure state, then most of the measurements that you make will have the same result as you would have had if the system had been at a finite temperature. That is, you don't have to do this micro-canonical ensemble or canonical ensemble. You just take one eigenstate, and most of the observables will be what you get from a thermal ensemble with probability 1 or something, right? So that's the eigenstate thermalization, and it is a hypothesis, right? So it's only demonstrated in, so maybe that's sort of what is happening here. Okay, I'd just like to spend a few minutes talking about what happens if you have a finite system now, because then this quasi-particle picture becomes kind of cute. Because then, if the world, our one-dimensional world, has periodic boundary conditions, which are a bit hard to make in the lab, but so it could have reflecting walls, okay, then what happens is these quasi-particles, this entangled pair of quasi-particles, this one, the right-moving one, can go all the way around the world here and emerge here and meet its friend at a certain time t, which will be basically L over 2v, or they can reflect from the walls and meet again at a time L over v. And at that point, if nothing, because you don't have right-left scattering in these models, they haven't lost their phase coherence, and when they meet again, they're just going to reconstitute the initial states. So this is an example of a quantum revival. One way to actually quantify this is to start from your initial state, evolve it with the Hamiltonian, and then just work out the overlap with your initial state. If you had perfect quantum revival, this return amplitude would just be 1. In general, it's going to be smaller than 1. It's more complicated than what I said, and here's an example of what you expect from when you quench to the critical point in what's called an Ising spin chain. And this is the logarithm of that return amplitude f. And it's normalized so that it sort of goes to a constant here. So a constant's been subtracted, and then you see that it decays very, very fast. And then it's got all this structure here. And the amount of structure that you get, this is actually kind of a fractal structure here, depends on how big your system is, as compared with the effective temperature, and you just get more and more structure here. There's a lot of beautiful mathematics here to do with the properties of modular functions. So those of you who know this. So all these features, though, can be understood within this quasi-particle picture. And I won't go through it, but for example, you see an interesting feature here in the middle. So the quantum revival should happen here, but you see it actually does not, and that's because this particular Ising model has 2 types of quasi-particles. It's due to this fermion description of the Ising model, and they actually destructively interfere, and you have to wait twice the amount of time before you get constructive interference. But you see all this other interesting structure here, and that happens, for example, here we can get 2 pairs of quasi-particles which constructively interfere, and that sounds great, except you realize that they only constructively interfere if this pair is entangled with that, and they're a distance apart of order L, which is much bigger than the initial correlation length here. So the probability or the amplitude for this happening is very, very small, which is why you do get a peak, but it's a small peak. Finally, it's interesting to understand, it helps us understand this so-called thermalization and how it relates to entanglement. So here I've drawn, once again, a space-time picture, now in a finite volume. And here I have various quasiparticles. So if you look at short times here, initially, then the fact that the system is finite doesn't really matter. What is happening is this green line here, which represents our interval, it falls inside the horizon here. So after then, it becomes thermalized, okay? And it starts to get more and more entangled. And so at the point when it gets thermalized, this green line is entangled with these blue lines here. But then as time evolves, nothing much happens to us, our system. It looks like it's actually in thermal equilibrium, but it gets entangled with a region of space which is retreating away at the speed of light. So if I look at the water in this jug, we would all agree that by now it's actually come to thermal equilibrium with the rest of the room. I would say that thermal equilibrium is in fact indistinguishable from what we would see if the whole universe were in a pure state and this were entangled with something, well, how long have I been talking for? Almost an hour. Okay, something that distance away. What's about an hour away? Is that Mars or Jupiter or somewhere? Okay, so yeah, okay. So it's a very interesting view of thermalization and the way that it actually fits in with our ideas of entanglement. Okay, I think I'll sort of stop there and miss out the last part. One important thing, but I'll just say briefly that one important thing that you need to do to make these calculations more believable is that you want to say, well, the conformal field theory Hamiltonian, we know this only describes the low energy states, and we're talking about high energy states. What justified you in actually doing that? So what you can do is sort of add extra terms to the Hamiltonian. And these extra terms are what are called irrelevant operators. They don't actually change the critical behavior. They don't actually change the low energy behavior, but they can certainly change the high energy behavior. And that's sort of hard to do in general, but one thing that you can do is to add terms which correspond to the square of the stress tensor. So the energy momentum tensor is an important operator in this theory, and so you can kind of study these, and they correspond to right, left, and left, right, and left, left, and right, right scattering processes. And if you think about this scattering as being due to the exchange of a particle, this particle is a particle that couples to the energy momentum tensor, and that's like a fluctuation in the metric, so, or a graviton. So this is like having scattering of the quasiparticles mediated by the exchange of a graviton, but not actually a massless graviton, but a very massive one. So it's like propagation in some kind of a random metric. And when I looked at propagation in a random metric and I Googled this, I got a picture which said gravitational lensing. So this is propagation of light from galaxies a long way away, as I'm sure quite a number of you in the room know. And the light sort of gets smeared because of gravitational lensing. And what this right-left scattering is going to do in our system is to sort of cause the light cones to sort of do a diffusive motion. So it's going to cause some kind of spreading of the light cones. And the revivals similarly get broadened. So let me just summarize. Quantum quenches give us a new and exciting way of probing dynamical behavior in many-body quantum systems. They can be realized in these sort of cold atom experiments. We get this horizon, this ballistic behavior. One thing that I didn't tell you, once you include this scattering, though, is the propagation speed actually depends on the initial states. So it's not universal. And that's what's observed experimentally. It makes us think about thermalization in a slightly different way. I don't think it's going to cause the textbooks on statistical physics to be revised, but it means that you might want to think carefully about what it means. There's this issue of integrability, that is what you can solve, whether it's justified to just look under the lamppost or not. And then there's some sort of neat stuff that could be seen experimentally also if you look for these quantum revivals in small systems. So I think I'll stop there, and thank you for your patience. Yeah.
What determines the time scale which this happens?
Oh.
This reaching the pseudo thermalization to this quench or fast Hamiltonian?
Okay, so the question is, what determines the time scale at which I start to see the thermalization? Well, it's a time scale which is longer than the speed of the quench. I assume I do this instantaneously, right? So what actually sets it depends on the size of the subsystem, right? So it's only subsystems which actually thermalize, and the time is the time it takes for a quasiparticle to cross the system once. So it's a very fast time, but not so fast as the speed with which you do the quench. Yeah. Yes, they do. And in particular, the fact that we deal with one-dimensional conformal field theories where the algebra of conformal transformations is in fact infinite dimensional. And that's due to the fact that any analytic function of a complex variable, as you know, corresponds to a conformal mapping. So analysis is really important here, and we use it in a very way. So I don't want to say that it's trivial that these results are trivial. And in particular, in higher dimensions, the same questions where you do have these extra global formal transformations which you don't have this infinite number of them. There we don't know. I mean, we can do calculations. It's very simple theory. Like coupled harmonic oscillators, basically. You know, free field theories. And then you do see this thermalization, which has been actually understood for a long time. But whether it happens more generally, I don't know. Within the ADS CFT sort of way of thinking about it, where you have conformal field theory on the boundary, and the way you do the quenches, you just dump in a bunch of energy, and or matter. And in the ADS spacetime, this just forms a collapsing ring, which may or may not then form a black hole. And if it does form a black hole, then it's just the Hawking radiation from this black hole, which is responsible for why you see a thermal state on the boundary. So from that point of view, thermalization is sort of perhaps easy to understand, though, than quantum, things like quantum revivals are then harder to understand, because then this black hole would somehow have to reverse itself, which it can't.
Well, this is really fascinating. In the case of CFT, of course, not in addition to this fixed, there are other quantum numbers like the wave.
Yeah, sure.
Is there any way of actually extracting that?
Yeah.
Quantum revival?
Yeah, sure. Actually, that very complicated graph that I showed you was due to interference between different quasiparticles carrying different conformal weights. So in a conformal field theory, as you know, there's a mapping between states and operators and all of this. So yes, it's all there in principle. So if you could observe these in detail, then you could pick out the conformal weights, for example. Yeah.
I guess I have a brief comment. Just, I mean, I think the level of confidence we have in these kinds of methods and in conformal field theories is such that we now believe that black holes do reverse themselves.
Well, that's one way of putting it, and I'm pleased.
They have to.
Yeah, sure.
Correct.
Yeah, but presumably these are not somehow classical. I mean, these kind of quantum revivals happen in conformal. Well, first of all, we're talking about two-dimensional, 1 + 1 dimensional conformal field theories, so the bulk is three-dimensional. So it's not okay. And the other thing is that these revivals happen in conformal field theories with a small value of the central charge and a finite number of conformal weights. And so the conformal field theories with large values of the central charge, which correspond to, which have a weakly coupled gravitational dual, then you probably don't get quantum revivals, and you get my guess is that you do get the formation of a black hole, and of a semi-classical black hole. But for small values of C, the bulk geometry would be some very strongly coupled quantum gravity, right? That you don't understand anyway, right? Or maybe I'm wrong.
But even at large central charge, you would expect to.
If you understand it in a revival way,
Yeah.
you probably have to cut the infrared. Right? That means that UV cuts off, you not see it. And to understand the revival way, you have to cut the UV.
But the recurrences will always happen just for unitary.
Yeah, but that means that it's unitary.
But I just want to say that what we're actually talking about here is a marvelous example of this interdisciplinary discussion between condensed matter physics and particle physics, and long may it continue.